So I'm gonna try to describe something which I think gives some confusion between galvanic and electrolytic cells, and that's the signs of these metals. So here we have an anode and a cathode, and largely the confusion is driven by the definitions of them. So anode, um, it's always where oxidation occurs, and cathode, it's always where reduction occurs. This never changes ever. And because oxidation is occurring at the anode, anodes are supposed to attract anions. And that's where its name actually comes from, is the fact that oxidation is occurring here, so anions are attracted to it. And anions have negative charge. Now, cathode, since reduction occurs at the cathode, and this is the gain of electrons, it's supposed to attract cations. And this is just the definitions of them. This is where they get their names from. So these always occur respectively, and this occurs as a result of their respective functions. Now, that explains why in a galvanic cell, we have a negative here and a positive here. Because if electrons are moving from the anode to the cathode this way, following this arrow, that means every time an electron is lost at the anode, there's room now for negative anions, which are in the water, to go towards this pole. And the same thing here. As electrons are gained at the cathode, that means the positive floating ions in the water will go here to balance out the negative charge gain. And this occurs because the anode and the cathode are spontaneously, we're having the electrons move from the anode to the cathode. Now, the reason they're switched in the electrolytic cell is because of electricity. So that's the only reason. So let's try to explain this. So normally, and remember I said redox never changes. So anode will always have oxidation occurring at it, and cathode will always have reduction occurring at it. That's what you can see here, because our electrons are still moving in the same direction. But here, there's a positive charge on this metal and a negative charge on this metal. And you're wondering why, right? So the reason is because it's not natural for this to occur. It's not spontaneous. That's what I mean by natural. This would not have occurred in the cell, meaning that normally this cathode, which is being reduced here, it actually has a lower reduction potential than the anode. This actually has the higher reduction potential, but you don't care. You just want it to go this way anyways. But if you want that, you're going to have to put some energy in. And another word for that is electrons. So what you're doing here is basically, this is an electron machine. And what it does is it supplies electrons. So what do I mean by this? Electrons normally move from the anode to the cathode. Why do they do this? Because we have more electrons naturally at the anode, which is why we lose them from the anode. Or I wouldn't say more electrons. I'm sorry about that. Let me rephrase that. The potential to lose electrons is greater at the anode. The potential to lose electrons is greater at the anode. So if the potential to lose electrons is higher at the anode, that means that we would naturally go this way in the galvanic cell. But here in this anode, electrolytic cell implies that this anode does not naturally have the more potential to lose electrons. It actually has a higher reduction potential, so to gain electrons. So actually, if this wanted to technically be galvanic, it could go this way, because this actually has a higher potential to gain electrons. but we don't want that to happen. And that's the whole point of an electrolytic cell, is that you're going the opposite way of spontaneousness. So what we do is, and I wish this, whatever this is, like, I guess that's why I called it an electron machine. I literally don't know what this is, but it's providing current. So actually, I'm going to draw it here so you can see what's happening. This is giving electrons this way, sending them into this guy. So now what we've done is we've artificially given this guy higher oxidation potential and lower reduction potential. Compared to this guy. So before it was flipped. This was how it is naturally, but we want it to go forward. So we use an outside source. Okay, so I'm going to erase the old stuff because that's not what's in this picture. The new stuff is what's in this picture. So let's go on and understand why that makes this positive and makes this negative. So if we're artificially providing electrons for this guy, and this machine is running the whole time, right? That means that every time an electron is lost, it's not like this situation where the electrons are lost, so therefore the anode becomes positive and attracts anions. No, that's not what happens. Because every time an electron is lost, electrons are coming from here in. So what happens is this stays negative and attracts positive. So in the end, this has a positive charge. So like, I know that's weird, like, oh, so it's negative, so it's positive, but you have to realize that these pictures, they depict after. There's a before and there's an after. And we never see the before in these pictures. We just see the after, which is why it can be confusing. It's not a full picture, it's a final picture. So what happens is this guy is losing electrons, but at the same time, he has a source here, which is pushing electrons. The only way this guy can lose electrons is if he has a source that's pushing electrons up his metal, because like he doesn't even naturally want to lose them, but he will if suddenly he has a bunch of supply of electrons, right? So that's why it's gonna have a positive charge in the end, because when the electrons are in one spot, electrons have negative charge, right? So that attracts positive. So you have to think in terms of always there's stuff moving. It's not like something's positive because it's positive or something's negative because it's negative. It's more like there's some type of there's a reason that it's positive, and that has to do with what it attracts to it. So if it's positive, it's because there was negative and it attracted the positive. So that's what I mean by final picture versus the before picture. So I hope that makes sense. So I can go ahead and explain the cathode as well, even though like all of these, my explanation is just going to be reversed here, but it's the same concept. So here the cathode is gaining electrons, right? So you're like, okay, it's gaining electrons, that's negative charge. Then why is it going to have a negative here? And the answer to that can also be explained by the electron pushing. So if the electrons are going in here, right, you would think, okay, so why isn't that attracting positive charge? But it's the same reason. There's electrons over here, a bunch of electrons, okay? And these electrons are always going to be attracting the positive charge. So if they're attracting all the positive charge, this isn't like this scenario where there's this thing. There's all this positive charge going this way. So if it keeps going this way, this guy's going to stay negative. And this is all because of this current thing supplied. So it's not going to attract the positive because there's always electrons coming here, which attract all the positive ions. So that leaves a bunch of negative ions. You know what I mean? So all the positive is here and all the negative is here.